What if the most powerful AI ever built could still never reach every truth? Not because it lacked data, because it needed more compute, not because its reasoning was too weak, but because the rules used to decide what counts as true placed a permanent boundary around what it could know. That is the idea behind my paper, The Limits of LLM Reachable Intelligence. The premise of this paper is that we may be able to do something like map the information space around a large language model. Given a particular training corpus, what information is reachable? What conclusions can a model derive from what it already knows? And from a security perspective, how close can an unclassified corpus bring us to classified or proprietary information? When I began thinking about these questions, I was reminded of a diagram from Douglas Hofstadter's Gödel, Escher, and Bach. It depicts a branching formal system surrounded by a larger unexplored space. We can imagine the axioms of that system as an LLM's training corpus. The branches represent conclusions that can be generated and verified from the starting assumptions. This is the white space, the region of reachable, certifiable information. But what does that say about the black space surrounding? What lies beyond the system's reach? And what are the theoretical limits of any attempt to map that boundary? To answer that question, I separate an AI reasoning system into two parts, the generator and the verifier. The generator is the underlying model. It produces a claim along with some form of justification. That justification might be a mathematical proof, a block of code, an experiment log, a compliance report, or a chain of logical steps. The verifier is the procedure that decides whether the justification is accepted. In mathematics, the verifier might be a formal proof checker such as Lean. In software engineering, it might be a test suite. In science, it could be a pre-registered experimental protocol and a statistical threshold. In an aligned large language model, the verifier might be a reward model trained from human preferences. The important assumption is that the verifier is fixed and computable. It follows explicit rules, always halts, and returns either accept or reject. This gives us a definition of what I call LLM reachable intelligence. The reachable set is not everything the model can say. Language models can say almost anything, including things that are false, incoherent, or unsupported. Instead, the reachable set consists of the claims that the model can produce together with the justification that the verifier accepts. This distinction reflects how AI systems are actually deployed. The model may generate a code patch, but tests determine whether it is accepted. It may draft a proof, but a proof checker determines whether it counts. It may produce a scientific explanation, but an experimental and institutional process determines whether that explanation becomes knowledge. The central argument is that this reachable set is inherently incomplete. First, if the generator and verifier are fixed, then the complete set of accepted claims is computably enumerable. In principle, a program could try every prompt, every random seed, and every possible output, run each result through the verifier, and gradually list everything the system will ever accept. Second, Gödel-style incompleteness tells us that no sufficiently expressive, computably enumerable formal system can capture every truth within its domain. Therefore, any fixed generator paired with a fixed computable verifier must miss some truths. This remains true regardless of how powerful the generator becomes. Future model might possess vastly more compute, better reasoning, a larger context window, and access to nearly every public document ever written. Yet, if its outputs must pass through a frozen standard of verification, there will still be true claims that the combined system can never certify. The limit is not merely a weakness of current models, it is structural. This does not mean that humans are generally more intelligent than machines, or that LLMs cannot be creative, useful, or even superhuman in many domains. It means that progress cannot come only from improving the generator. Humans can complement AI systems because humans participate in changing the standards themselves. Mathematicians introduce new axioms. Scientists develop new instruments and revise their models. Legal and political communities redefine what counts as acceptable evidence. Organizations update policies when their existing rules produce bad outcomes. Humans can re-axiomatize. We can replace the verifier, expand it, or decide that an entirely new kind of evidence should count. Human institutions can participate in an open-ended process of revising the system under which claims are evaluated. This has direct implications for attempts to map informational reachability. A reachability map can show what is derivable under a particular corpus, model, and verification regime. It can identify paths through which seemingly harmless information may be recombined to reveal protected ideas. But the map will always be conditional. It maps reachability inside a particular system. Change the model, introduce a new inference method, add new evidence, or revise the verifier, and the frontier moves. The black space is not simply information that the model has not reached yet. Some of it may be unreachable under the current rules of acceptance. The long-term challenge, then, is not merely to build more powerful models. It is to design verification regimes, update processes and governance systems that determine how the boundary of certified knowledge should expand. The future of intelligence may depend as much on who controls the verifier as on who builds the generator.